Welcome to Week 3, Module 11 of the Database Management Systems course in the IIT Madras online BSc program. In the last week, across all 5 modules, we did a detailed introduction to the fundamentals of the relational database model attributes, types, and the basic mathematical structure that we'll dig into more deeply later on. We talked about schema, instance, different types of keys and basic operations like select, project, and join, the fundamental operations of relational algebra. We also introduced the basic structure of queries, both for the data definition language and the data manipulation language, using several features of SQL, select, from, where, and various extensions on top of that. We show how to form a range of queries, relatively simple ones, and we also covered different set operations, the use of null values, aggregation functions, and more. So it was quite an active week, covering the relational database model and SQL. We'll start this week with a quick recap of what we covered. This recap isn't about simply restating what we learned last week. Instead, we'll try solving an example for most of the major features we discussed. This is important because now is the time to actually start practicing coding in SQL. As you've seen, it's a kind of programming language, but a very different style from anything you've done before, which has mostly been procedural in nature. SQL is the first declarative language you're working with, based on a very different underlying model. Unless you practice a lot, you won't really internalize the mechanisms for writing queries, modifying database structure, or manipulating rows, and going forward, that will make things much harder. So today we'll do a quick roundup of some key examples. We'll continue using the same university database schema from last week, so you can refer back to that anytime. Let's start with the basic select. Given a relation, you want to extract some information from it. From the classroom relation, we want to find the names of buildings that contain classrooms with a capacity less than 100. Since we are working with the classroom relation, the from part of the query is immediately clear from classroom, meaning we are working with the classroom relation. Then, we want classrooms whose capacity is less than 100. In this relation, there are 3 attributes: room number, capacity, and building. Even without seeing the schema explicitly, common sense tells us room number is the key here, since a building can have multiple classrooms, and multiple classrooms can easily share the same capacity. So, in the where clause, our condition, or predicate, is that capacity is less than 100. That restricts us to classrooms meeting that condition. Finally, in the select clause, we specify what we actually want, the names of the buildings. So we write a select building. As you've learned, a basic select from, where query returns a multiset by default, meaning duplicates are not removed. Here, we specifically want to remove duplicates, so we add a distinct qualifier. The full query becomes a select distinct building from classroom, where capacity is less than 100. Going through the table, it checks each row for capacity less than 100. This one doesn't qualify, this one does, this one does, this one does, this one does. So among the qualifying rows in terms of distinct buildings, we get Painter, Taylor, Watson, and Watson again. Naturally, since we want duplicates removed and we're using distinct, one of the 2 Watson entries has to go, leaving us with our final output. The result is a table with a single column, building, containing 3 rows. This is the simplest and most common form of select from, where, and by itself, it covers a huge portion of the queries you'll write. Now, if instead we didn't want to remove duplicates, the query looks almost identical, except instead of saying distinct, we can explicitly say all. That means the same 4 rows are selected by the where clause. We take the projection onto building, but this time the repeated Watson is not removed, so we get 2 instances of Watson in the output. It's worth emphasizing, and I'll keep repeating this so it really sinks in, that select from, where returns a multiset by default. So even if you don't write all explicitly, you'll still get repetitions by default. Nothing gets removed unless you specifically add distinct. Saying all is really just an explicit way of confirming give me everything, but it's optional, since that's the default behavior anyway. To actually remove repetitions, you need to include distinct. So that's the simplest kind of query you can write, and you can keep track of our progress as we move along. Next, let's talk about the Cartesian product, select from, where actually covers both projection and selection, two operators from relational algebra. A Cartesian product comes into play when you're working with two or more relations. Let's look at an example involving two relations, student and department, where we want to form all combinations of rows between students and departments. If we simply wrote select name budget from student, department, without any where clause, it would give us every possible combination of students and departments. But instead, we've added a condition saying that the department name from the student relation must equal the department name from the department relation. This ensures we only keep the rows where the student's department actually matches an existing department, meaning that student genuinely belongs to that department. This is really a Cartesian product combined with a filtering condition, and as you'll see later, this is exactly what a join operation accomplishes more directly, something we'll introduce in a later module. We're also asking specifically for students across all departments where the department's budget is less than $0.1 million, that is, $100,000, so the budget has to satisfy that condition as well. If you check back against the two example relations we gave earlier, you'll see exactly which rows survive this filtering. In the final output, we show the student's name, not the department's name, since we're projecting only the name and the budget, and in every surviving row you can verify the budget condition holds. This was a slightly more advanced query, since instead of using one relation, we're now combining two. Let's take this a step further using the renaming feature, using the keyword as. You can rename any attribute or relation to something else. In this example, we rename the student relation as S, and the department relation as D. Writing as is technically optional. You could just write student S and department D, and it would mean the same thing, but I prefer being explicit, since that reduces the chances of errors. Now we can write S.department name equals D.department name, without needing to fully spell out student or department each time, saving a bit of typing. In the select clause, we write S.name, which refers to student.name because of this alias, and we rename this attribute as student name. Similarly, budget gets renamed as department budget. You'll notice I could have written this as D.budget instead, since budget belongs to the department relation, but I don't strictly need to specify that. Because the budget attribute only exists in the department relation, it doesn't appear in the student relation at all. Department name, on the other hand, appears in both relations, so there we do need to distinguish whether we mean the department name from the student table or from the department table. These are just stylistic choices, and yes, I could equally well have written D.budget here instead. This is simply another way of writing the same query, and as things get more complex, especially when you need to take the cross product of a relation with itself, you'll definitely need to rely on renaming, as we've already seen. Now, within the where clause, your predicate can use any Boolean operator and, or, and not. Let's look at an example. We want to find the names of all instructors whose department is finance, or whose department building is Watson or Taylor. Since we want instructor names, the instructor table has to be included in our from clause, and since we also care about department buildings, the department table needs to be included too. So, in the from clause, we have two relations, instructor and department. What condition connects them? We need to know each instructor's department, so we require the department name of the instructor to match the department name in the department table. Exactly the same idea as we used earlier with students. So the first part of our where clause becomes d.department name equals I.department name. After renaming, this is our base join condition, ensuring the instructor and department rows are properly correlated. Then, on top of that, we specify that either the instructor's department is finance, meaning I.department name equals finance, or the building is Watson or Taylor. Here, we use the in-clause building in Watson, Taylor. This means the condition is true if the building's value is either Watson or Taylor, and false otherwise. Using in here simplifies things considerably, since otherwise we'd have to write out building equals Watson or building equals Taylor explicitly, which is more verbose and more error-prone. If you look carefully at how this query is structured, you'll notice that the join condition must always hold for the query to be valid at all, and everything else forms the additional filtering condition. That's why we use and between the join condition, wrapped in parentheses appropriately, and the rest of the filter, which itself uses or internally, since we want either finance as the department, or Watson or Taylor as the building. If you omit these parentheses, the query becomes ambiguous or outright incorrect, since you'd end up with a confusing mix of ands and ors, and you'd have to work out the exact order of evaluation. So whenever you combine multiple connectives like and, or, and not, it's best to use parentheses deliberately, matching the intended logical structure. That's how this particular query is constructed. Next, we looked at using strings, which let you match a variety of value patterns. Here we have a table of courses, and we want to find the titles of all courses whose course ID starts with exactly 3 letters representing the department. Since some course ID have 3 letters, others have 2, followed by a hyphen and then a number. How do we express exactly 3 letters? We want exactly 3 characters before the hyphen, so we use 3 underscores, followed by a hyphen, and then a wildcard % to allow anything after that. This pattern matches courses like this one, and this one, but not this one, since that course ID has only 2 characters before the hyphen. Using this pattern, entries from departments like CS, E, or MU, which use 2-letter codes, get excluded, and whatever remains, we then project onto the title column, giving us the titles of the matching courses. So this shows how flexible and powerful string pattern matching can be. Next is ordering your output, which is fairly intuitive. Order by simply arranges your result rows according to whichever attribute you specify. By default, it sorts in ascending order, though you can explicitly write ascending if you want to be clear. It's optional, but for descending order, you do need to explicitly specify that. In this example, we're ordering by 2 attributes first, department name in ascending order, meaning alphabetical order by department, and then, within each department, total credits in descending order. So, for instance, biology comes before computer science alphabetically, and within computer science specifically, the rows are further sorted by decreasing total credits. If we reversed the order of these 2 sorting criteria, putting total credits first, the result would instead be sorted primarily by total credits, and only within equal credit values would it then be sorted by department name. So with order by, it's important to think carefully about exactly which ordering you actually want among your attributes. We've already discussed the in operator, so I won't repeat that. Feel free to review it on your own. For set operations, we have 3 union, intersection and set difference, which in SQL is called except. Let's look at union first. Suppose we want to find all courses offered either in fall 2018 or in spring, and combine those into one overall set of courses. Keep in mind that union, unlike select, is a true set operation, not a multi-set operation, so it automatically removes duplicates. If you actually want to preserve duplicates, meaning courses offered in both semesters should appear twice, you'd need to use union all instead. Similarly, we have intersect. Here, we want the names of all instructors who taught either in the computer science department or in the finance department, and whose salary meets a certain condition. We express the department condition using in, so that either value is acceptable, giving us all instructors whose salary is less than 80,000. This effectively behaves like an and condition across the two criteria. Using intersection, we keep only those instructors who satisfy both conditions simultaneously, being in computer science or finance, and having a salary under 80,000, and that combined intersection is exactly the result you'll see if you check against the given table. I'd definitely encourage you to verify these results against the tables we provided. Similarly, using except we again want the names of instructors from computer science or finance, but this time we want those whose salary is either less than 70,000 or greater than 90,000. Here, we compute this using except we start with the full list of qualifying instructors and then subtract out those who don't satisfy the salary condition. Of course, you could also express this using a more complex where clause directly, but when there's a clear notion of forming two separate sets and combining them, expressing it through set operations is often much easier to understand. Finally, let's talk about aggregation, which is fairly straightforward. The key thing to remember is that aggregation typically requires grouping by whichever entity you're aggregating over. In this example, that entity is the building. From the classroom table, we want to find the name and average capacity of each building. Since we're grouping by building, we group all rows sharing the same building together, then compute the average capacity for each group. We've also added a condition that we only want buildings whose average capacity exceeds 25. So for each building, we compute the average and only keep it in the output if that average is greater than 25. Otherwise it's excluded. In this particular example, it turns out Painter doesn't appear in the final output. That's because Painter has only a single classroom, so its average capacity is simply that one value, which happens to be 10, well below the 25 threshold, so Painter is filtered out. Similarly, you can compute minimum, for example, to find the minimum salary, or maximum, to find the maximum number of credits. I'd encourage you to work through these using the example table yourself, and confirm they behave as expected. Finally, there's count, which simply counts the number of rows. For instance, from the section relation, we want to find the number of courses offered in each building. Since we're computing this per building, we group by building, and then count the number of course ID within each group. Grouping puts, say, all the Taylor rows together, and then we count how many course entries appear within that group. In this case, it turns out there are 5 such courses in that particular building, so the count comes out to 5. Note that even if some course ID repeat, they're still counted individually as separate rows, since we're simply counting however many rows exist in that group. And finally, sum, which is used to compute totals. For example, here we're finding the total credits offered by each department. Working from the course table, grouped by department name, we sum up the credit values within each group. So, for instance, if we look at music, there's only a single entry, so the total is simply 3. For biology, there are 3 separate entries, 4 plus 4 plus 3, giving a total of 11 credits for biology. These results come out in whatever order the grouping naturally produces, but if we wanted, we could add an order by clause on department name to get the results sorted alphabetically, biology, then computer science, and so on. That's really just a matter of choice. That wraps up a quick roundup of the most common and widely used foundational elements of SQL. I'd strongly encourage you to practice a lot of examples. There will be tutorials and practice problems provided as well. So make sure you build real confidence with these basics. As we move further through this week, you'll see more advanced SQL features that let you accomplish even more interesting things. Thank you very much for your attention, and let's continue our discussion of SQL in the next module. Welcome to Module 12 of the Database Management Systems course in the IIT Madras online BSc program. In the last module, we walked through examples covering the introductory, basic part of SQL. Starting from this module, we move into what I'm calling intermediate SQL. Once you understand the basic query structure and how it works, you build on that in intermediate SQL to accomplish genuinely more useful things, and eventually you'll move on to some advanced SQL features as well. Today, we'll talk about two basic but very powerful features. The first is, quite obviously, essential data manipulation. So far, we've only been talking about queries that retrieve existing data as it is, but how do we add records, remove records, or change the value of some attribute? That's data modification. The second feature is the powerful mechanism of nested subqueries, where one query can appear as part of the condition or as part of another query. Recall that the SQL select from, where structure is the backbone expression, we work with a set of attributes on the select line, a set of relations in the from clause, and a predicate, potentially quite complex, in the where clause. Now, in any one of these three parts, we can replace a particular item with a subquery. An attribute can be replaced by a subquery that produces a single value, or a relation in the from clause can be replaced by any valid query. Remember, the input to a query is one or more relations, but the output of a query is always a single relation. So, since any query's output is itself a relation, we can use that output as a relation inside the from clause of another query. That's the nesting idea. Alternatively, we can use a subquery inside a predicate condition in the former attribute, some operator, and a subquery, where the operator will be defined shortly. That's the basic structure. A subquery can appear as part of the where clause, as part of the from clause, or as part of the select clause. Let's start with the where clause. A typical subquery there is used to perform set theoretic checks, set membership, comparisons, or cardinality checks. There are other uses too, but these are the typical ones. Let's revisit an example from the last module, finding courses offered in both fall 2009 and spring 2010. We solved this earlier using intersect. Now let's look at it from a different angle, going back to the fundamental definition of intersection itself. Setting aside a bit of the query for now, focus on just this first part. This represents the set of courses offered in fall 2009. Previously, using intersect, we found the set of courses offered in spring 2010 and combined the two sets by intersecting them, keeping whatever was common. But we can check that same commonality differently. A row that shows up here obviously represents a course offered in fall 2009. Then we ask, does that exact same course ID also occur in the set of courses offered in spring 2010? That's a set membership check, using in, the same idea we used earlier when checking distinct values across fall and spring. So the second part represents the set of course ID offered in spring. If the course ID chosen here, meaning it's offered in fall 2009, also belongs to the spring 2010 set, then it clearly belongs to both, and so it becomes part of the answer. So you can think about this either as literally intersecting two sets directly, or, equivalently, as taking one set, and for every element in it, checking whether that element also belongs to the other set, keeping it if so and discarding it otherwise. That's exactly the same logic, just expressed as a predicate. This part in parentheses is our nested query, and it's worth stressing that a nested subquery can't stand entirely on its own. It's always a nested part of some larger enclosing query. Similarly, finding courses offered in fall 2009 but not in spring essentially our earlier except example, can be written by simply adding a not here, since we're now saying the course belongs to fall 2009, but does not belong to spring 2010. So that's another example of the same nested subquery pattern, just used slightly differently. Subqueries can be genuinely powerful. You can perform set membership checks that go beyond a single value. For example, find the total number of distinct students who have taken a course section taught by a particular instructor. How do we get there? We express this using a nested query. That nested query tells us, given the instructor's ID, which courses that instructor has taught. A student may or may not have taken one of those courses. If they have, they should be counted in the final result. If not, they shouldn't be. So this represents the set of courses taught by that instructor as tuples of course ID, section ID, semester, and year taken from the takes relation. That tells us, for any given student, which courses that student has actually taken. If a student's course tuple belongs to that set of courses taught by the instructor, then that student has indeed taken one of that instructor's courses and should be counted. That's a set membership check involving an entire tuple, not just a single value. Then, since a student might appear multiple times, we take distinct student ID and count them. The rest of the query, admittedly, could be written more simply, but the point here was to show that set membership checks can involve entire tuples, not just single values. There's an additional layer of semantics here too. Consider this: find the names of instructors whose salary is greater than that of some instructor in the biology department. This doesn't mean the instructor's salary has to beat everyone in biology. Maybe it only beats 5 people there. It just needs to be higher than at least one biology instructor's salary. If an instructor's salary is lower than even the lowest paid biology instructor, that instructor won't be included. Here's how we express this. We need to select from the instructor table twice, since both department information and salary live in that same table. This is essentially a self-join. We need the condition that one instructor's salary is greater than another's, provided there exists at least one row where that second instructor's salary is lower, and that second instructor belongs to the biology department. So we take the set of biology instructors and check every instructor's salary against them. We can make the intent even clearer using a subquery. The subquery gives us the list of salaries of biology department instructors. And then, for every instructor overall, we check whether their salary exceeds at least one of those biology salaries. That semantics is expressed using the keyword SUN. So here, we get a one-column relation listing biology salaries, and we check whether a given instructor's salary is greater than at least one value in that list. If it's greater than none of them, that instructor's name is excluded. This is a good moment to briefly revisit predicate logic. If you've studied it before, this will be familiar. If not, it's worth reviewing. If you have a comparison, less than, greater than, or any of the 6 standard comparisons, combined with some over a relation, it essentially means there exists at least one row in that relation for which the comparison holds true. If no such row exists, the whole expression is false, but if even one qualifying row exists, the expression is true. This is known as existential quantification, since sum essentially represents the existence of at least one matching value. For example, consider whether 5 is less than some value in a given relation. If the relation contains a 6, then yes, this is true, since there exists at least one value, namely 6, that's greater than 5. On the other hand, if the relation only contains a 0 and 5, then 5 is not less than some of them, since neither value in that set exceeds 5. So this would be false. If we ask whether 5 equals some value in the relation, and the relation does contain 5, then yes, this is true. And if we ask whether 5 is not equal to some value, and there's a 0 present, This is also true, since 5 is indeed not equal to 0, so sum is used to express existential quantification within predicate logic in many practical situations. Naturally, alongside existential quantification, we also have universal quantification, expressed using all. For example, find the names of all instructors whose salary is greater than the salaries of every instructor in the biology department. This is structured almost identically to before. We build a list of biology salaries and compare against it, but this time using all, meaning every single biology salary has to be lower than the instructor's own salary for that instructor to be included in the result. This means all essentially represents for all if you take every single row of a given relation. The condition must hold true for every one of them. Only then is the overall predicate considered true. I should clarify something here. All actually corresponds to universal quantification, not existential. Please note that correction if you're taking notes. Let's look at some examples. Is 5 less than all values in a relation containing 6? No, since it's not less than 6 itself, so that's false. Is 5 less than all values in some other relation? If it's genuinely less than both values there, then yes, that's true. Is 5 equal to all values? That would be false unless every single value equals 5. Is 5 not equal to all values? That would be true if 5 doesn't match any value in the relation. For instance, if the relation contains 4 and 6, 5 isn't equal to either, so that's true. So this shows how existential and universal quantification can both be expressed using nested queries combined with the sum and all qualifiers. There's another useful construct for checking whether a relation is empty, called exists. The exists construct returns true if there's at least one row present in that relation. Essentially, if you did a count on that relation and got a value greater than 0, exists would be true, otherwise, it's false. Similarly, not exists is true precisely when there are no rows at all, meaning the count is 0, or the relation is empty. This can be used quite cleverly in various situations. Let's revisit our earlier example again, finding all courses taught in both 2009 and 2010, expressed yet another way. In some cases, choosing between these different styles really comes down to personal preference or coding style. In other cases, as we'll see later, certain ways of writing a query can be considerably more efficient than others. And you should also keep in mind that, unless there's a pressing performance need, it's often best to write queries in a way that's easy to read and understand, since ultimately it's people who have to debug and maintain this code. So, back to finding courses offered in both semesters. This part represents courses from fall 2009. We need to check whether each of those same courses is also offered in spring 2010. So we filter for semester spring, year 2010, and check whether the exact same course ID appears there too, since, in the back of our minds, we're really trying to compute an intersection. If a given fall 2009 course does show up in spring 2010 as well, then this inner subquery will return a non-empty result, meaning at least one matching row exists. But if that particular course wasn't offered in spring 2010 at all, then there will be no matching row, and the inner query result will be empty. That's exactly the condition we check using exists. So, we take courses from the outer relation, which represents fall 2009 courses, and check whether that same course, matched by course ID, also appears among the spring 2010 courses, that is, whether that inner set is empty or non-empty. If it's non-empty, that course gets selected. That's a really elegant use of exists. The correlation here happens through a shared alias linking the outer query to the inner query, which is why we call this a correlated subquery. The inner query correlates back to values from the outer one. Just as we have exists, we also have not exists, which simply asserts that a given set must be empty. There's an example combining not exists with a subquery that itself represents the difference between two other queries. I'll let you work through that one on your own, and of course, feel free to come back with questions if anything's unclear. There's also a way to check for uniqueness of values. In a subquery, using the keyword unique, the condition evaluates to true only if every returned row is genuinely distinct. Otherwise it's false. So far, we've focused on subqueries within the where clause, but you can also place a subquery inside the from clause, which is often even simpler. For example, find the average salary of departments whose average salary exceeds 42,000. Here, the subquery itself computes the average salary per department, and then we just perform a straightforward select from, where on top of that result, you can combine conditions freely here too, as we've seen elsewhere. Essentially, this inner computation becomes a relation in its own right, which we use directly in the from clause. So we're selecting from a temporary relation containing department name and average salary, computed directly from the instructor table, and from there, we filter using our average salary condition, without needing a having clause at all. We had actually solved the same problem earlier using having, so this is simply an alternative approach, worth exploring on your own. There's also a with clause, and its underlying idea is simple. Suppose our basic goal is find the departments having the maximum budget, meaning we select department name from department based on the maximum budget value. Using with, we first compute a subquery that finds the maximum budget from the department table, treat that resulting value as a small temporary table, let's call it max budget, with a single attribute, value. Then, we use this temporary table later in our main query, comparing each department's budget against that maximum value. So it essentially lets you create a temporary named relation upfront, which you can then reference throughout the rest of your query. In effect, this becomes part of your from clause conceptually, but it's defined earlier, since you need to create the temporary relation before you can actually use it. There are more elaborate examples using the with clause that I'll leave for you to explore on your own. You can also embed subqueries directly within the select clause, but remember, select always expects individual attribute values, so any subquery used there must be a scalar query, meaning it must return exactly one single value. For example, list every department along with the number of instructors in that department. Here, we place a subquery directly within the select clause, appearing before the from clause of the outer query. What does this subquery return? It counts how many instructor rows match a given department by comparing department names between the department table and the instructor table. That comparison yields a single count value for each department, how many instructors belong there, and we label that resulting field number of instructors. It's important that this kind of subquery always returns exactly one row, one single value. If it doesn't, you'll get an error. Having covered that, let's move on to modifying databases. There are three basic operations here: delete a row, insert a row, or update a row. These are conceptually similar to select from, where, but the syntax differs somewhat. For delete, if you want to remove every row from a table, you simply say delete from that table. Otherwise, you can add a where clause with a predicate, so that only matching rows get deleted. For example, this deletes all instructors belonging to the finance department. Any row satisfying that condition gets removed, or delete all instructor rows where the department is located in the Watson building. Here we use a nested query, first finding which departments are located in Watson, and then deleting any instructor belonging to one of those departments, expressed quite simply. So when deleting, your conditions can be as simple or as complex as any other where clause condition, including nested subqueries. Here's a subtlety worth examining carefully: delete all instructors whose salary is below the average instructor salary. It seems straightforward, Just compute the average salary using a nested subquery and delete anyone below that threshold. But there's a real problem here. Since we're modifying the very table we're computing the average from, the moment we delete one qualifying instructor, the average salary itself changes. Suppose there were originally 10 instructors with some average salary, and one instructor qualifies for deletion because their salary is below that average. Once you delete that instructor, you're left with 9 remaining instructors, and their average salary is now different from before. So, since deleting rows changes the average salary as we go, this naive query won't behave as intended. What's the fix? You need to separate these two steps. Otherwise, you're simultaneously modifying a table and basing your condition on values that keep shifting as a result of that same modification. Instead, you should first compute the average salary using a nested query or some other mechanism, store that as a fixed value, and only then delete every row whose salary falls below that fixed value. These are exactly the kinds of subtleties you need to watch out for. Insert works in a broadly similar way, but the syntax is insert into a given relation, followed by values, and then a tuple of values. These values need to match the order in which the attributes were originally defined when the table was created, otherwise you'll get an error. Alternatively, you can explicitly specify the attribute names alongside the insert statement, in which case your values just need to match the order you specify them in, which is quite convenient. You can also insert rows with null values. For example, if a student's total credits aren't known yet, you can simply insert null there. Alternatively, you might default that value to 0 instead, as shown in an example where we select ID, name, and department from the instructor table, and insert those values into the student table, while explicitly setting total credits to 0 since that information isn't available for these particular rows. Again, there's a subtlety to watch for when insertion involves modifying the very table you're selecting from. The where clause and select portion of an insert statement get fully evaluated first, before any actual insertion happens. Otherwise, something like inserting into a table by selecting everything from that very same table would cause it to keep inserting endlessly. Finally, updates let you modify field values. You write update, followed by the relation, and then, using set, specify the new value for a given attribute. For example, an update statement might give a 3% raise to instructors earning more than 100,000, while another statement gives a 5% raise to those earning 100,000 or less. But if you try to combine both of these into two separate update statements, one after another, you might run into subtle problems, because the first update has already changed some salary values by the time the second update runs, potentially affecting who qualifies under each condition. A cleaner way to express this is using a conditional structure. If this condition holds, do this, otherwise do that, essentially the familiar if-else logic from procedural programming, expressed in SQL using something called a case statement. You'd write something like set salary equal to case when a certain salary condition holds. Use this new value, otherwise use this other value. This way, everything gets computed and applied in a single, consistent pass, without running into the earlier problem. These are all features designed to make writing queries considerably easier. You can also perform updates using scalar subqueries, remembering that a scalar query is one that returns exactly a single value. There's an example of this too. I won't walk through every step here. I trust you'll be able to work through the logic yourself, and of course, feel free to reach out if you get stuck. So, in today's module, we introduced nested subqueries in SQL, and we also covered the core data modification features delete, insert, and update. Thank you all very much for your attention, and we'll meet again for the next module on SQL.
Welcome to Module 13 of the Database Management Systems course in the IIT Madras online BSc program. We've been discussing intermediate-level features of SQL. In the last module, we covered two very important groups of features: One was nested subqueries, where the output of one query can be used as part of the from clause, as part of the predicate in the where clause, or even within the select clause, which makes writing many queries conceptually simpler and semantically clearer. We also covered the basic data modification features of SQL: delete, insert, and update. Today, we'll continue with intermediate features, focusing on two more important topics: joins and views. We've already talked about performing joins using the select from where structure, and that certainly works. But it often becomes much easier if we use explicit join expressions to connect to relations directly and produce a new resulting relation. As we've seen, a join operation is essentially a Cartesian product, but with certain conditions, requiring that rows from the two relations actually match in some way. Depending on exactly what condition you apply, you get different classes of joins, and, much like select, a join can also specify exactly which attributes should appear in the final result. It's also quite common, though not universal, for join expressions to be used as a subquery within a from clause, so you've joined your two relations, established relationships between attributes that originally belonged to two separate tables, and now you use that combined relation for further computation. That's a particularly powerful use case for joins that we'll explore more later. There are several different types of joins between relations. Rather than explaining each abstractly, we'll work through an example of each to make things clear. Let's start with the cross-join. This exists mainly for completeness. It's simply a straightforward Cartesian product of rows from the tables involved. For example, selecting everything from an employees table and a department table using a cross-join means taking every row from employees and every row from department and pairing them in every possible combination. So if you have m employee rows and n department rows, you end up with m times n total rows, combining all the attributes from both tables. This is an explicit way of expressing that operation, mainly for completeness and semantic clarity, since the same result would happen implicitly if you simply wrote select everything from employee, department. Cross-join itself isn't especially interesting. What's genuinely interesting is what comes next. Let's use a small example to illustrate the different join types. We'll work with two relations, course and prerequisite. The course relation has course ID as its key, along with title, department name, and credits. The prerequisite relation has course ID and prerequisite ID, with course ID again being a key. So course ID is common between the two relations. The course table tells you everything about a course's properties, while the prerequisite table tells you about its prerequisite. Notice the specific choices in this example. A biology course 301 has a listed prerequisite. A computer science course 190 also has a listed prerequisite, but another computer science course 315 has no entry at all in the prerequisite table, meaning its prerequisite simply isn't known. Meanwhile, in a prerequisite table, there's an entry for a course numbered 347, whose prerequisite we do know, but that particular course doesn't actually appear in the course table at all. This kind of information gap happens constantly in real databases. We want to join course and prerequisite in the presence of this incompleteness and see the different ways this join can meaningfully be defined. The first type is called inner join. This joins naturally on course ID, as you'd expect, keeping matching rows where the course ID are equal, and discarding anything that doesn't match. So the missing entries, the unknown prerequisite for that one computer science course, and the missing course details for that other course number, are simply dropped entirely. Within a join, you're left with only the courses that appear in both relations, in this case, just the biology course and the first computer science course. Looking at it in terms of sets of course ID, Inner join essentially gives you the intersection, exactly what's common to both. We could also specify this as a natural join. If we do, you get all the attributes from the course table plus all the attributes from the prerequisite table, everything combined, 4 attributes plus 2 attributes, giving a 6 total. But if it's specified as natural, the attribute or attributes used for the join, the ones where equality was checked, get merged into a single column rather than duplicated. So specifying natural means that shared course ID column appears just once in the result, rather than twice. Without the word natural, that duplication is preserved. Both copies of the shared column remain. This inner join is the most conservative approach when information is incomplete, but naturally, we're losing information in the result. We've dropped some courses entirely, and we've dropped prerequisite information for others. What if we don't want to lose that information? We might not know everything, but we still don't want to throw away the fact that our unmatched computer science course genuinely exists just because we don't know its prerequisite. Or, similarly, we don't want to discard the known prerequisite information for the unmatched entry just because we're missing other course details like its title. Instead, we can fill in unknown values with null. This gives us a more inclusive result, a bigger combined relation. This is the idea behind outer join. Outer join comes in 2 main flavors, a left and right. Picture our earlier inner join result as the overlapping portion between 2 sets, one representing the left relation, the other representing the right relation. A left outer join ensures that every row from the left relation is included in the result, and if there's no corresponding match on the right side's attributes simply get filled in with null. So, using our example, we retain both matching rows from the inner join as before, but we also keep our unmatched computer science course, which has no entry in the prerequisite table, filling its prerequisite ID with null, and of course, that column has to allow null values for this to work. This guarantees that every row from the left relation appears somewhere in the final result. If we specify this as natural, that duplicate course ID column doesn't appear twice. If we don't specify natural, it does, exactly as before. So a left outer join preserves information from the left relation, and naturally, there's a corresponding right outer join that preserves information from the right relation instead. With a right outer join, our previously unmatched prerequisite entry, the one whose course doesn't appear in the course table, is now retained, with nulls filling in for all its unknown course details, since we don't actually know its title, department, or credits, but we do have its prerequisite information. Since this is a right outer join, our unmatched computer science course from earlier doesn't appear here at all, since it belonged to the left relation and has no match on the right. Again, specifying natural means the duplicate course ID column doesn't appear. Since we have both left and right variants, we can naturally choose to include both simultaneously, and when we do that, it's called a full outer join. So, to summarize inner join, left outer join, right outer join, and full outer join, and each of these can be combined with conditions like natural, or a specific predicate, or matching on a chosen attribute rather than assuming matching column names. You could even join on attribute X from one relation matched against attribute Y from a different relation, or restrict the join to only a particular subset of attributes. Here's what a full outer join looks like in our running example. We have the shared, matching portion from the inner join, then the extra row contributed by the left outer join, and the extra row contributed by the right outer join. So, everything from the left relation is included. Everything from the right relation is included too. One null appears for the unmatched left entry's missing prerequisite, and 3 nulls appear for the unmatched right entry's missing course details. All information is preserved, giving you the complete overall picture. Depending on the situation, context, and the specific semantics you need, you'll decide which type of join makes sense. And again, remember to specify natural if you don't want the duplicate course ID column showing up. Let's look at some concrete syntax examples. You might write a course in a join prerequisite on some condition. That on clause specifies exactly what you're joining on. Without an explicit condition, it would still join based on matching column names, but this shows you can add an explicit condition, potentially combined with and, or, and so on, forming a more complex predicate. This connects to something we'll cover more thoroughly when discussing relational algebra alongside plain joins and natural joins. There's also something called a theta join, which is simply a join with an additional condition attached. For instance, joining naturally but restricting results to only courses from the biology department. So, this shows a predicate-based join, and since it's not marked natural, you'll see two separate course ID columns in the result. That's the key difference compared to a natural join, where that duplicate column would be merged into one. Similarly, you can do a left-outer join with an explicit condition, which behaves like our earlier example since natural wasn't specified, so the duplicate course ID column appears, but this illustrates how to attach predicates alongside a join. Here's another example: a course, natural, right-outer join, prerequisite. Since natural is specified here, the duplicate course ID column doesn't appear. And another example: a full outer join, prerequisite, using course ID. This using syntax means that whatever attribute you specify, in this case, course ID, must exist in both relations, otherwise it wouldn't make sense. Course ID happens to be the shared identifier here, and there might be other shared attribute names too, but you specifically want only course ID to participate in the join condition, so you explicitly name it using. This gives you a full outer join based specifically on that shared course ID attribute. So you can write joins without any condition at all, with an explicit predicate condition, or using the using keyword, and each approach produces its own particular result. This is genuinely important, because join is really the primary way to explicitly and clearly link information across two or more tables, but it also carries serious performance consequences, because, fundamentally, a join starts from a Cartesian product. If you have 10 rows in one table and 20 in another, that's only 200 combined rows to compute and then filter down. But if you have 1,000,000 rows in each table, 1,000,000 squared becomes 1,000,000,000, or 10 to the 12th, combined rows, an enormous number, even though your final filtered result might end up being just 10,000 rows. That massive intermediate cross product can be absolutely crushing computationally. So join sits in this interesting space, extremely expressive and powerful, easy to write conceptually, but potentially very expensive to execute. This means we need smarter strategies to get the same correct result while doing far less actual computational work than a naive, literal join would require. We'll return to these performance aspects later, exploring different variants and alternative ways of writing equivalent queries that avoid letting intermediate results blow up. Now, let's move on to a second very interesting concept of use. Recall that early on, we talked about 3 layers of data abstraction. There's the physical layer, dealing with actual bits and bytes, which we haven't covered yet and will discuss in a later series of modules. There's the logical, or conceptual layer, which is what we've been working with all along. And on top of that, there's the view layer, which isn't data as it's physically stored, but rather data as it's perceived or presented to a particular user. Often, you don't want to expose an entire table to every user. You don't want to reveal your full logical model, or grant access to every piece of information to everyone. Most people working with course management need to deal with instructors, departments, students, and so on, but you probably don't want most of these users to see an instructor's salary, or perhaps even a department's budget. So what do? You create a view, Creating a view works very much like writing a select statement. A select statement takes a full table and gives you back a projected, filtered version of it, selecting certain columns and certain rows to produce a new table. A view works similarly, except that a view is a virtual relation. Let me explain what that means. You write create view, give it a name, and define it as some query expression, which could be a select statement. That's how a new view comes into existence. The key difference is that when you create a table, that table gets physically created, and any inserts, updates, or deletes you perform get persisted, staying there until you explicitly change them. A view isn't like that at all. It's really more like a stored expression. Every single time the view gets used, the underlying query expression that defines the view gets evaluated fresh, and whatever relation results from that evaluation becomes what you see through the view. So a view is inherently dynamic. It isn't stored in your database at all, yet anyone using it experiences it as though the relation genuinely exists. In reality, though, it's produced purely through computation, not physical storage. Let's look at some concrete examples. Suppose we're working with the instructor table, and we want to hide salary information. We write a query expression selecting instructor ID, name, and department name, 3 fields typically needed for academic purposes, from the instructor table, our original, persistent table. This could actually be a view too, but for now, let's treat it as a genuine base table. Then we say a create view faculty as this query. Now, faculty behaves just like a table, with columns for ID, name, and department name. Crucially, this view doesn't include the salary column at all, and it doesn't even expose the fact that such a field exists, since it's entirely hidden behind the underlying query expression. How do you actually use this view? Simply treat it like any other relation. For example, suppose we want to find the names of instructors in the biology department. We now have this new, faculty-based view of instructors. So we select name from faculty, where department equals biology. Notice that you're extracting information without ever needing to know that the underlying instructor relation even exists. The key point, always, is that since faculty is a virtual relation, it isn't stored persistently. The underlying instructor table might be continuously changing, so there's no persistent, separately stored copy of faculty data sitting around. Every time you query it, it effectively triggers the underlying query behind the scenes, much like a nested query, constructing a faculty relation fresh, and then running your outer query against that freshly constructed relation. That's fundamentally how views work. Once you understand this core concept, everything else about views is really just common sense extended a bit further. You can even create views that include computed information. For example, a view showing department name alongside total salary, a completely virtual relation with no corresponding physical table, but computed dynamically whenever it's used. Each time you query this view, the underlying nested query involving aggregation, like summing salaries, gets executed fresh, producing the resulting rows you see. As we've seen, views can be used to help construct further queries, and naturally, that also means views can be used to build other views. For instance, imagine a view representing all physics courses offered in fall 2009, something you should now find quite straightforward given everything we've covered. We can then build another view on top of that one. When you use this second view, the system needs to instantiate the first view underlying it, and if that first view itself depended on yet another view, the system would keep expanding recursively, working backward through the chain until it reaches actual physical relations, computes everything needed, and finally produces your requested view result. This dynamic expansion process is called view expansion. Essentially, you can build a view on top of another view, on top of yet another, mixing views and genuine physical relations freely, without needing to worry, at any given moment, about which pieces are physically stored tables and which are purely virtual views. In our example, we have one nested query in the from clause and an outer query on top of it applying an additional condition, say restricting results to courses in the Watson building. That's the actual result you'd get from defining this narrow view based on our earlier Physics in Fall 2009 view. Eternally, the system expands this definition automatically, constructing the necessary intermediate view, and evaluates everything at the moment it's actually needed. Since view expansion allows one view to depend on another, we say that a view relation depends directly on another view relation if that second view is used in defining the first one. In our example, the Fall 2009 physics view is used directly in defining the Watson-specific narrower view, so there's a direct dependency there. This dependency chain could also be transitive, one view depending on a third, which depends on a fourth, which depends on yet another, forming a longer chain of dependencies. All of this works perfectly fine, as long as a view never ends up depending on itself, which would be called a recursive view. View expansion typically works through a repeated process. Find any view referenced within the current expression, replace it with the query expression that defines it, exactly as we saw going from the Watson-specific view back to the underlying Physics in 2009 view, and if that expression itself contains further views, keep repeating this substitution until no views remain, only genuine base relations. As long as view definitions aren't recursive, this process is guaranteed to eventually terminate. That doesn't mean recursive views are impossible. Recursive views are actually a rich and fairly deep topic within databases and SQL, but we won't be covering recursive views in this course, since they require background in recursive function theory that we haven't built up yet. That said, not all recursive views are useless. Some genuinely elegant recursive views do exist, but we're deliberately skipping that deeper territory here, which is why I flagged it earlier as an area we're not fully covering. Now, an important question, since we're treating a view like a relation. What happens if we try to update it? Suppose we attempt an insert into a view. Since a view isn't physically stored, that insert can't actually happen directly against the view itself. It's just an expression, a query. Instead, any insert has to ultimately be translated into an insert against the actual underlying physical relation. So, if you insert into our faculty view, providing ID, name, and department, but the underlying instructor relation also has a required salary field, this insert will only succeed if that salary field is allowed to be null. If it is, the actual instructor relation gets a new row inserted with the given ID, name, and department, and a null salary. If that's not possible, the insert simply can't go through. There are genuine complications with updating views, though, because some updates simply can't be uniquely translated back into a clear, unambiguous change to the underlying physical relation. Consider this scenario. Imagine a view combining instructor ID, name, and building, derived by joining instructor and department information together. If you try to insert into this combined view, providing just an ID, a name, and a building, there's a real problem. You haven't specified which department that instructor belongs to. If that particular building happens to house multiple different departments, which department name should the system actually use for this new instructor? And if no department at all is currently associated with that building, what should it use then? There's simply no clear, unique way to resolve that ambiguity. Because of situations like this, updates through views are typically quite restricted. Most SQL implementations only allow updates on relatively simple, single relation views, meaning the view is based on just one underlying relation, and its select clause only includes attributes directly from that relation. Nothing overly complicated. It's worth checking your specific database system's documentation to understand exactly which kinds of view updates it permits. In general, though, it's not great practice to frequently update views. It's best treated as an occasional operation rather than routine. There can also be cases like this. Suppose you have a view specifically representing history department instructors, and you try to insert a row into that view specifying the department as biology instead. That simply can't work, since allowing it would immediately contradict and invalidate the very definition of that view. One final point: even though a view is inherently virtual, you always have the option, at any point, to materialize it. That means physically creating an actual table containing whatever rows the view currently represents, essentially freezing a snapshot of it. But once you do that, that materialized table naturally becomes disconnected from the view's ongoing, dynamic nature. The underlying view definition might keep changing as underlying data changes, but your materialized snapshot won't automatically reflect those future changes. So if you materialize a view, you'll need some mechanism to keep it updated over time if you want it to stay accurate. So, today we've covered join expressions and views in SQL at the intermediate level. Thank you all very much for your attention. I'll see you in the next module, which will be our final module in the intermediate SQL series, where we'll cover a few more remaining topics.
Welcome to Module 14 of Database Management Systems in the IIT Madras online BSc program. We've been discussing intermediate level features of SQL, following the introductory material earlier. In the last module, we covered two very important features of joins, including various types like inner and outer joins, natural joins, and so on, and views. Another important feature that lets you build a virtual relation out of one or more actual relations, or even out of other views, and expose this to users for restricted, controlled use. Today, we'll cover several more intermediate topics of transactions, integrity constraints, some additional data types, and authorization. Each of these is critical in its own way, and together, they bring us much closer to being able to use SQL for real, practical database applications. Let's start with transactions, something we've mentioned briefly before. Formally, a transaction is a unit of work, some meaningful task we want to perform, and it's defined to be atomic. Atomicity means that a transaction, which might consist of one or more SQL statements executed together as part of some larger task, such as transferring funds between accounts, enrolling a student, or registering for a course, either completes entirely and correctly, or, if something goes wrong partway through, gets rolled back entirely. This atomic property is absolutely critical for keeping the database in a consistent state at all times. Transactions also need isolation from other transactions running concurrently, since many transactions will often be operating on the same tables at the same time, and the outcome of one transaction shouldn't improperly affect the outcome of another. We'll discuss isolation in much greater depth later on. Transactions begin implicitly, but they end explicitly, either by committing the work, finalizing it permanently, or by rolling it back, undoing everything done so far if some error occurred, returning the database to its previous, consistent state. Many database systems default to committing automatically, though this behavior can typically be turned off, whereas rolling back is always something you trigger explicitly, in response to detecting some problem. Transactions are a genuinely central topic, and we'll dedicate an entire separate series of modules to exploring atomicity, isolation, and the broader set of properties known as acid properties in much more detail. Next, let's talk about integrity constraints. We touched on these somewhat during database design, but there's more to add here. These constraints exist to guard against violations of basic real-world rules, or conditions within the database itself that we want to preserve and prevent from being tampered with. Real-world examples might include requiring a checking account to always maintain some minimum balance, requiring an employee's hourly salary to meet some minimum wage threshold, or requiring customer records to always include a non-null phone number. There are many other kinds of integrity constraints that a database might need to enforce as well. Typical integrity constraints on a single relation include things like requiring a particular attribute to never be null, enforcing a primary key, enforcing general uniqueness, or applying a check clause that verifies some custom predicate. You've already encountered some of these. Not null constraints let you declare that a particular attribute can never contain a null value. You can similarly declare a set of attributes as unique, meaning that combination of values across those attributes can never repeat across the table's rows, essentially guaranteeing no duplicates, which is exactly the definition of a candidate key. This differs from a primary key in one key way. A candidate key is still allowed to contain null values, whereas a primary key can never be null, so uniqueness alone is a somewhat weaker constraint than being a primary key. A check constraint lets you enforce additional business logic beyond simple structural rules. For example, consider the section table in our university database, where the primary key is a combination of course ID, section ID, semester, and year. We might want to ensure that semester can only take specific, valid values, say fall, winter, spring, or summer, assuming those are the recognized semester names in this context. In some educational systems, say in India, the relevant terms might instead be autumn and spring only. Either way, we want to restrict semester to just a fixed, valid set of values. A check constraint accomplishes exactly this, using something like semester in this specific list of four allowed values, which is really just a set membership check. If someone tries to set semester to anything outside that allowed set, this integrity constraint gets violated, and that insertion or update simply won't be permitted. This preserves the integrity of what values are actually allowed in that field. We've also previously discussed referential integrity, which governs consistency between two or more different tables. For example, suppose the instructor table contains an instructor whose department is listed as biology. It's necessary that the department table actually contains a corresponding entry for biology. The department table itself isn't literally part of the instructor table, but the instructor record references biology as a department name value, so we need the department table to genuinely contain a row where the department name is biology, so we can look up further details about the department when needed. Conceptually, this makes sense. If someone claims affiliation with a department, and that department doesn't actually exist in the table describing all valid departments, that's an inconsistent state. This is exactly the concept of a foreign key. The department name field in the instructor table becomes a foreign key referencing the department table. Let's look at the consequences of this kind of constraint. We define it by saying that the department name attribute in the instructor table references the department table, making it a foreign key. Now, since these are two independent tables, changes, inserts, deletes, and updates can happen to each one independently, but that independence can lead to inconsistency. For instance, suppose an instructor's department is biology, and biology exists in the department table. Now suppose someone deletes the biology entry from the department table entirely. This immediately creates inconsistency, since the instructor's department reference would now point to something that no longer exists. So, this foreign key constraint needs an accompanying policy specifying exactly what should happen in that situation. One option is a policy called onDelete cascade, meaning that if the biology entry is removed from the department table, the deletion cascades automatically, and any course entries referencing biology as their department get deleted too, as a chain reaction. Similarly, you could specify on update cascade, so if the biology department's name changes to, say, ioscience, that change automatically propagates to every course entry referencing that department. The database handles updating those references for you. This kind of cascading foreign key constraint ensures proper referential integrity is consistently maintained. There are other available policy options too, such as taking no action, setting the reference to null, or setting it to some default value. This is a genuinely critical aspect of good database design. There are also subtler integrity violation scenarios that can arise during transactions. For example, consider a person's database containing individual people, their ID and names, along with fields for mother and father. Suppose we have referential integrity constraints, foreign keys, on both the mother and father fields. Interestingly, in this case, the referential integrity constraint reference is the very same table, person. What does this mean in practice? It means that whenever you insert a new person record, whoever is listed as that person's mother or father must already exist somewhere in that same table. So how do you actually perform an insertion without violating this constraint? One approach would be to insert a person's mother and father before inserting that person themselves. Alternatively, if these fields allow null values, you could simply leave them null initially. Both approaches have their own issues. If null isn't allowed, you can't take that second approach at all. And even with the first approach, inserting parents before their children, that same requirement scales further, since each parent's own parents would similarly need to be inserted beforehand, and this chain has to terminate somewhere eventually. If null values aren't permitted anywhere along that chain, you'll eventually need some designed mechanism to break that chain deliberately. Another possible option is to defer constraint checking until later. There are specific strategies for handling that, which we'll discuss at a later stage. Now let's move on to SQL data types and schemas. You're already familiar with many basic data types, like numeric types, integers, and character types such as char, but SQL also includes several composite, built-in data types worth knowing. Among the most important are date and time types. You can represent a date in various supported formats, represent a standalone time, or represent a timestamp, combining both date and time together. The difference between two dates, or between two timestamps, is called an interval, representing some span of time, perhaps a single day, or any other duration, and intervals can be added to or subtracted from date and time values directly. This makes date and time manipulation quite convenient, something you'll need constantly in nearly every real database application. Another important type of database object is an index. Indexing is a genuinely deep topic that we'll return to in much more detail later, but let's introduce the basic idea here. Suppose we have a student table with an ID field, a 5-character variable length string serving as the primary key, which is inherently unique. In that context, it's possible to create an index, explicitly named, using a statement like create index, give it a name, on the student table, using the ID attribute. Indexes are essentially separate underlying data structures, often based on structures like B-trees, that help dramatically speed up database record processing, particularly searching for specific records. For instance, since ID is a primary key, searching for a student with a specific ID should return exactly one matching row. Without an index, the database would potentially need to scan through every single row checking for a match. With an index, that search can typically be done in logarithmic time relative to the total number of rows, or sometimes even faster. Using this additional supporting data structure, we'll cover how indexes actually work, and how they're maintained in a separate, dedicated discussion, but for now, just know that indexing represents another important data-related concept within SQL. Another feature is user-defined types. These aren't quite user-defined in the deepest sense. They're more like convenient aliases you can create for existing types, along with certain associated properties. If you're familiar with C or C++, this is conceptually similar to a typelef, giving a particular data definition a meaningful name. For example, you might write create type, naming it $, define as a numeric type with 12 total digits and 2 decimal places, and then use that new type name whenever defining relevant attributes elsewhere. The most valuable reason for doing this is improved semantic clarity. If you simply declared a budget field as a generic numeric type with 12 digits and 2 decimal places, it's genuinely unclear what currency that value represents: euros, dollars, rupees, pesos, or something else entirely. By giving that type a meaningful name, you make your schema significantly easier to understand and maintain. But user-defined types extend well beyond just improving readability. They also lead naturally into something called domains. Domains are essentially user-defined types too, but domains can additionally carry attached constraints. For example, you might create a domain called person name, which, on its own, might just be a simple alias for a 20-character variable length string. But critically, we can also specify that it must never be null. This means that whenever you declare an attribute using as person name domain, you automatically get both the correct underlying type and the guarantee that it can never be null, without needing to explicitly restate that constraint every single time. This kind of pattern is extremely common in practice. Useful name formats, standard constraints, and so on can all be captured once in a shared, reusable domain. Domains can also incorporate check constraints. For example, you might define a degree-level domain as a 10-character variable length string, constrained specifically to only allow one of a small set of valid degree-level values. Domains become extremely useful for creating well-constrained, reusable data types across your entire database design, giving them consistent names you can rely on throughout your schema. This naturally improves semantic clarity, while also making your overall design much more convenient and consistent to work with. Essentially, these become reusable data types you define once and use everywhere. There are also some other specialized data types worth knowing, called blob, meaning binary large object, and glob, meaning character large object, used to store large binary or textual data, such as images, videos, and similar content. These aren't typically stored directly within the database itself. They usually live in the underlying file system instead, but the database maintains a reference pointing to that external data. So when you access a field containing a blob, you don't get the raw data itself directly. You get a pointer leading to where that data actually lives. This approach lets databases effectively manage even fairly unstructured data alongside their normal structured records, and that's the essence of these large object types. Finally, let's talk about authorization. It's clearly important to ensure that not everyone can freely view or modify every part of a database. There are several distinct types of authorization, applying to different parts of the database, or different kinds of operations. Some of the most common authorization types include read, insert, delete, and update permissions, essentially basic read and write authorization. Anyone trying to read data needs appropriate read authorization. Anyone attempting to update values needs update authorization, and so on. There are also authorizations governing operations on the database schema itself, like the indexing feature we just discussed. Not everyone should necessarily be permitted to freely create new indexes, since creating and maintaining an index carries real costs. Indexes don't change the underlying data itself, but they can significantly affect overall database performance, so it's important to restrict who's actually permitted to create them. Similarly, permissions are needed to control who can create entirely new relations, alter existing relations by adding or removing attributes, or drop relations altogether. Essentially, across all the various schema-related operations we've covered throughout SQL, most of them require some appropriate, specific form of authorization, depending on exactly what kind of operation is being performed. Authorization is granted through what are called privileges. A privilege is essentially the authority to perform some specific action. You grant a particular privilege on a given relation to a specified list of users. That's the fundamental mechanism behind authorization. Let's look at a concrete example. Suppose we have a privilege called select. What does granting this actually mean? Fundamentally, it represents read authorization. Granting select access lets someone read data from one or more relations. To grant this kind of read authorization, you use the basic command grant, specifying the privilege, which here is select, the table you're granting it on, say, the instructor table, and finally, the specific users you're granting it to. This could even be granted to public, meaning literally everyone gets that access. Though that's fairly uncommon in practice, you might instead grant it to specific named roles, something we'll discuss shortly. Similarly, there are privileges for insert, delete, and so on, following the same basic pattern, grant insert on, and so forth, or you could grant all privileges at once, meaning the recipient gets full access to every available privilege type. Naturally, since privileges can be granted, they can also be revoked. Authorization is a two-way street. When you revoke a privilege, you're essentially cancelling it, perhaps because someone has left the organization entirely and no longer has any business accessing the database at all, or perhaps they've simply moved off a particular project. A person might still retain authorization for 10 other tables, while having their access specifically withdrawn for just these 2 particular tables. Revocation follows a similar structure, specifying which privilege you're revoking, say, the select privilege, which relation it applies to and which specific list of users, sometimes called the revokee list, is having that authorization removed. You might specify all if you want to revoke every privilege at once, and the revokee list could similarly include public, meaning everyone loses that particular privilege, except, naturally, for the person actually performing the revocation themselves. It's also worth noting that whoever is granting or revoking a privilege must themselves already hold that privilege, along with the specific additional privilege of being allowed to grant privileges to others. Otherwise, imagine the problem. Anyone could simply grant themselves arbitrary privileges freely, which clearly shouldn't be possible. So there's a special, distinct privilege specifically governing whether someone is allowed to authorize others at all. You can also define roles for authorization purposes. Rather than managing permissions individually, imagine a development team consisting of 20 engineers, all of whom, as a group, need broadly similar types of authorization. Instead of individually granting every single privilege to every single person separately, which quickly becomes unmanageable, you can instead define a role representing that development function, specify exactly which privileges that role requires, and grant those privileges collectively to the role itself, rather than to individuals. For instance, you might grant select access on the takes relation directly to a role, rather than to a specific named user. Then, to add a particular person into that role, you'd write something like grant instructor to Amit, where Amit is a specific user. Once Amit belongs to the instructor role, and various privileges have been granted to that role, Amit automatically inherits all of those privileges through membership. Roles can also be granted to other roles, forming a hierarchy. For example, suppose you have a role called teaching assistant, and you grant that role to the instructor role. This means the instructor role now inherits every privilege associated with the teaching assistant role too, effectively becoming a strict superset, though not the other way around. This lets you build up hierarchies of roles, where a person's overall privileges reflect everything granted through every role they hold, directly or indirectly. For instance, you might create a dean role, grant the instructor role to the dean role, and then grant the dean role to a specific person, say, Satoshi. This means Satoshi ends up with every privilege associated with being a dean, which itself includes every privilege associated with being an instructor, so anything granted directly to the instructor role becomes available to Satoshi as dean, and anything granted specifically to the dean role is also available to Satoshi, but wouldn't be available to someone who only holds the instructor role without also holding the dean role. That's the fundamental mechanics of how roles work. Authorization can also be granted specifically on views, not just on base tables. For example, you might create a view using some particular query, say, a view showing certain geography department instructor information, and then grant select access on that specific view to a role, say, a geo staff role. This means that whenever geo staff members issue a select statement against that view, they're able to retrieve results successfully. What's particularly interesting here is that geo staff members are being granted permission specifically on the view itself. They might not have any direct select permission on the underlying instructor table at all, yet they're still able to query this particular geo instructor view successfully, and that's precisely the elegance of using views this way, since whatever sensitive information the view intentionally hides remains hidden from geo staff, exactly as the view is designed to do. So certain users might indeed have direct select access to the full instructor table, while geo staff specifically don't, but they're granted access to this particular restricted view instead, and through that view they're still able to perform their necessary select queries. These are exactly the kinds of nuanced distinctions worth keeping in mind. There are several other authorization features worth mentioning as well. Authorization itself is genuinely a substantial topic. For example, you can grant a references privilege, specifically the privilege to create foreign keys referencing a particular table. This is essentially a schema-level authorization, since it governs whether someone is permitted to set up a foreign key constraint, a referential integrity relationship, involving the table. This might be important for certain users who need to enforce some particular consistency requirement that wasn't originally accounted for in the initial schema design. Finally, privileges themselves can be transferred to others. For example, you might write something like grant select on department to Amit, giving Amit select authorization specifically on the department table, and then add with grant option. This additional clause means Amit can now further grant that same select privilege onto someone else as well. This illustrates that the ability to authorize others can itself be granted, extended to specific users, roles, and so on. Similar considerations apply to cascading revocations, or restricting revocations, and various related nuances. These all follow similar underlying patterns to what we've discussed with revocation more generally. So, that wraps up our discussion of authorization. In this module, we've covered 4 genuinely key areas of transactions, which form a fundamental building block of database systems, integrity constraints, which are essential for maintaining consistency. We'll return to both of these topics in much greater depth later on, additional data types beyond the basics, and finally, the broader topic of authorization, which we'll likely revisit further in later modules as well. Thank you all very much for your attention, and I'll see you in the next module. Welcome to Module 15 of Database Management Systems in the IIT Madras BSc Online program. So far, we've been covering intermediate-level SQL features, building on the introductory material. In the last module, we discussed transactions, integrity constraints, additional data types, and authorization. In this module, I want to walk you through some additional features that, while maybe not absolutely critical for the initial design of smaller applications, are genuinely powerful tools that extend SQL's capabilities substantially. I'd categorize these as SQL's advanced features, and they include functions and procedures within SQL, along with a very important feature called triggers, which we'll explore, including what they mean and what kind of performance implications they carry. Now, don't be surprised. I did promise earlier that SQL is a declarative language, and it is, but it also has procedural extensions, and we'll talk about those now. There are two basic ways to combine SQL with procedural logic. One approach treats SQL as a query language and uses a separate, general-purpose programming language, like C, Java, or Python, referred to somewhat oddly as the native language, though I'm not entirely sure why that particular term stuck. In this model, you have a collection of independent programs, functions and variables, written in that native language, which you can invoke directly from SQL, passing data to a function and getting a result back. This is often called embedded or extensional programming using SQL, and all interactions with the database still flow exclusively through SQL's query processor. The other model works the opposite way. Instead of these being independent, SQL statements get embedded directly within the native language's program code. So you might be writing a C function, and at certain points within it, you embed actual SQL commands directly. This is a more tightly embedded style of programming. Again, all actual database transactions still flow through SQL's query processor, but here, the surrounding native program controls exactly when SQL operations get invoked and how results get collected. Over time, SQL itself has evolved to include its own built-in function and procedural features, allowing you to do a great deal of procedural programming directly within SQL itself, without needing any external native language at all. This capability was introduced in the 1999 version of the SQL standard, which I mentioned earlier when discussing SQL's history. So functions and procedures can be written either directly in SQL itself or in an external programming language, following either of the two models we just discussed, whether that's C, Java, Python, or something else. Why would you still want an external language interface if SQL already supports procedural extensions? The main reason is that functions written in an external language are particularly valuable when working with specialized data types, images, geometric objects, or when implementing genuinely complex algorithms. If you want to build something with a real object-oriented design, that's quite difficult to achieve cleanly within SQL's procedural extensions alone, whereas it's very natural in a language like C++ or Java. Using external programming this way lets you take advantage of those richer design capabilities as part of your overall database operations, which is genuinely useful. Another notable feature is what's called a table-valued function, meaning a function in SQL that can actually return an entire table, rather than just a single scalar value, which is what functions typically return. As we'll see, there are several supporting constructs for this. Let me first walk through how basic functions and procedures work, and then move through the remaining constructs a bit more quickly, since they closely resemble familiar constructs from imperative languages like C or Java, sharing very similar logical structure and control flow, even though the exact syntax differs slightly. Details you can always look up in the reference manual as needed. Let's start with defining functions. In SQL, essentially everything begins with the keyword create, so you'd write create function, give it a name, and specify its parameters, each with a name and a type. These aren't table attributes, they're specifically function parameters. The return type is specified separately, using the keyword returns. For example, a function called something like department count might take a 20-character string as a parameter and return an integer. Then, between begin and end, you write the actual function body. Within that body, you can declare local variables using declare, giving each a name and type, and then include a plain SQL query. For instance, the function body might run a query like a select count of all matching rows into a local variable, counting how many rows in the instructor table have a department name matching the parameter passed into the function. So, if you pass in, say, physics, It checks the instructor table's department name column for matching rows, counts however many match, stores that count in your local variable, and then returns that value, using the keyword return. Notice, without the s this time, the trailing s only appears in the returns keyword when declaring the return type, not when you actually return a value partway through the function body. That's the essential structure of a function. Here's how you might actually use such a function. Suppose you want to find departments with more than 12 instructors, and you want to see their name and budget. Selecting department name and budget from the department table is straightforward, but how do you express the more than 12 instructors condition? You use your department count function directly within the query, passing in the current row's department name as its parameter. This function computes the matching count and returns it, and you check whether that returned value exceeds 12. If it does, that department's name and budget get included in your final output, otherwise, that row gets excluded. Notice how closely this declaration structure resembles what you'd write in an ordinary imperative language, aside from some syntax differences, and it illustrates the basic mechanism for exchanging data between a procedural, variable-based computation and SQL's declarative select from where structure. This shows how a computed value can be seamlessly incorporated directly into that select from where structure, essentially bridging the declarative and procedural sides of the language. That's the core idea. Everything beyond this is really just a matter of syntax, but conceptually, you should already understand what's happening. So, fundamentally, you can think of a function as a kind of parameterized view. I could, technically, have created a view computing that same count, but a view's definition is fixed. I'd have to hardcode a specific department name. It couldn't vary as a parameter. With a function, that department name genuinely becomes a variable parameter, making it a parameterized view of sorts, useful in many other contexts as well. Table functions, meaning functions that return an entire table, work in a fairly straightforward way. Instead of specifying a single scalar return type, you specify the complete structure of the resulting table, just the attribute names and types, without needing to specify any constraints, and then, in the function body, you provide a query whose result matches that promised table structure exactly. That entire resulting table gets returned when the function is called. To actually use a table function, say one called instructor of, which takes a department name and returns a table of matching instructors, if you pass in, say, music, to make it clear to SQL that this represents a table produced by a function call, rather than a literal stored table, you write from table, explicitly signaling that a table-valued function is being invoked here, and its resulting table gets incorporated into your surrounding select query. Naturally, alongside functions, you also have procedures, which don't return any value at all. A procedure can have any number of parameters, and those parameters can be designated as input parameters, output parameters, or potentially both, but crucially, there's no return value involved, no returns clause at all. The overall structure is otherwise quite similar. For instance, you might have a department name coming in as an input parameter to a procedure, explicitly qualified with the procedure's name to indicate it's a procedural parameter being passed directly in, and a separate output parameter, say, a count value, that gets set as part of the procedure's internal SQL logic. There's no explicit return statement here either, since there's no specific single value being returned. Instead, you simply assign the output parameter's value as part of your procedural logic. When execution reaches the end of the procedure body, control automatically returns to whoever called it, and that output parameter's final value becomes available to the caller. To use this, you'd declare an integer variable, and then invoke the procedure using the keyword call, explicitly signaling that this is a procedure, not a function, since procedures, unlike functions, can't appear as part of a larger expression. Earlier, when we used from table, that syntax made it clear a function was being invoked implicitly within an expression, but a procedure can't be embedded that way, since it has no return value, so you invoke it explicitly using call, passing in your input parameter, say physics, and once the procedure computes the count, that result becomes available through your declared output variable. So, SQL supports both functions and procedures, and interestingly, just like in C++ or Java, SQL functions and procedures can also be overloaded, meaning you can reuse the same function or procedure name multiple times, as long as the parameter lists differ, either in number of parameters or in their types. There are several typical procedural language constructs available as well, and I'll run through what's available, though I strongly encourage you to consult your specific database system's manual whenever you actually use these, since function and procedure support varies quite a bit across different database systems. Many don't strictly follow the standard, and while they generally support similar kinds of constructs, the exact names, syntax, and even certain semantic details can differ noticeably between systems. The first construct is naturally a compound statement, which you've already seen using begin and end. Anything placed between begin and end is treated as a single combined statement, much like how Pascal grouped statements, or how C and C++ use curly braces for the same purpose. There's a while loop, structured as while some Boolean condition do, followed by a sequence of SQL statements, and finally closed with end while. Similarly, there's a repeat construct. With a while loop, execution continues only as long as the Boolean condition remains true, meaning the loop body might not execute even a single time if the condition starts out false. A repeat loop, on the other hand, always executes its body at least once, running a sequence of SQL statements repeatedly until some Boolean condition becomes true. One small syntactic quirk here, compared to typical languages, where you'd often see something like repeat, until directly, SQL instead requires an explicit end repeat to close off the loop scoop separately. There's also a for loop, which feels more similar to something you might see in Python, rather than the more elaborate structure found in C. You'd write something like for rs, followed by an SQL query, say, selecting budget values from the department table. Here R represents the relation resulting from that query. Within the loop body, you can perform a procedural assignment, marked using set. For instance, suppose you've declared a local variable n, initialized to 0, and inside the loop, you increment it by each row's budget value. This continues for every row present in that budget relation, represented by R, accumulating a running total across all matching budgets. You also have standard if then else conditional constructs if some Boolean expression, then some action, optionally followed by else if conditions, and an optional final else clause as a default fallback. These closely mirror conditional constructs from any procedural language you're already familiar with, so I won't dwell on detailed examples here, since you're likely already quite comfortable with this kind of conditional logic from other languages. There are actually two variants of the case statement. The first closely resembles a switch statement in C. You write case followed by a variable, and then a series of when clauses, each specifying a particular value. If the variable equals one particular value, a corresponding sequence of statements executes. If it equals a different value, a different sequence executes instead, and everything wraps up with end case. This works essentially just like C's switch statement. There's also an interesting variant called a searched case, where instead of writing a simple variable after case, you write, within each one clause, a full expression that evaluates to a particular value. This expression can be virtually any valid SQL expression, and whatever result it evaluates to gets matched against each case's expected value, triggering the corresponding sequence of statements. This means anything expressible using the simple case form can also be expressed using searched case, but not necessarily the other way around, making searched case a considerably more powerful and flexible construct than what's typically available in standard procedural languages. SQL also supports exception handling. You can raise an exception explicitly using Signal, and whenever you raise an exception, it must have an associated handler defined somewhere, specifying exactly where control should go and what should happen next once that exception occurs. You can define your own custom handlers, or rely on certain default handlers that are already built in. For example, consider declaring an exception representing a situation where a classroom has run out of available seats. You're trying to enroll more students than the room can actually hold. The natural handling policy here might be an exit handler. Exit handlers are a predefined SQL construct that simply terminates whatever enclosing begin-end block was executing when the exception occurred and exits cleanly. That's how you'd declare this particular exception and associate an exit handler with it whenever your procedural logic encounters a scenario matching that exception condition. Say, the classroom is genuinely full and you're still attempting to add another student. You'd explicitly signal that exception, which immediately terminates the current execution block and transfers control to the associated handler. Since we specified an exit handler here, nothing further happens beyond simply terminating cleanly, though other, more elaborate handlers and exception types certainly exist. I won't go into further detail on those here, since they're really just additional, optional features beyond the core concept. Finally, as mentioned earlier, you can define procedures and functions implemented in an external language, and this is relatively straightforward syntactically. You'd again use create procedure, which is nothing new, but the body specifies a different language, say, C, along with an external reference indicating exactly where that compiled function can be found, essentially a file path pointing to its location. Procedures and functions implemented this way, in an external language, can then be invoked from SQL just like any other procedure or function. There are real benefits to this external language approach. Certain operations become considerably more expressive, semantically clearer, and potentially more efficient as well. But there are also genuine risks involved, since you're effectively handing control outside the database system entirely into an external execution environment, which introduces possibilities for accidental data corruption or genuine security vulnerabilities. Because of this, careful security precautions, such as sandboxing, are often necessary. You'll often want to favor languages considered relatively safe, meaning languages that are inherently harder to exploit or break. For example, C is generally considered quite unsafe in this regard, particularly many of its string handling functions, which are notoriously easy to exploit through buffer overflow style attacks, potentially exposing access to unrelated data. Modern C does provide somewhat safer alternative versions of these string functions now. Java, by comparison, is considered relatively safer, since it never grants direct raw memory access. Everything routes through the Java virtual machine instead, providing an additional protective layer. So there are meaningful trade-offs to consider here. Using external language routines can genuinely boost efficiency, but that efficiency often comes at the cost of reduced security guarantees, so this needs to be handled carefully and deliberately. Now let's shift to something quite different, though equally critical for good database design: triggers. Let me first explain the underlying concern that motivates triggers. A great deal of what we do involves simply reading data, and reading data, whether the results are good or bad for whatever purpose, has no lasting consequence on the database itself. But the moment you actually modify data through an insert, an update, or a delete, you need to ensure that various other things remain properly consistent as a result. For example, if you delete something, you might need to record that deletion somewhere else, to know later who performed that action, useful for tracing back and auditing purposes down the line. So, insert, delete, and update are collectively referred to as events. Whenever one of these events occurs, though not necessarily every single time, we might want to automatically trigger some corresponding action, perhaps modifying some other related data, or flagging some kind of notification message, or really anything appropriate. Triggers are frequently used to enforce data integrity, supporting referential integrity constraints, or check constraints, and to update other related tables automatically. For instance, if you need cascading behavior of some kind, this is exactly the underlying mechanism that makes it possible. To specify a trigger, you need to specify which event it responds to, exactly when it should fire, either before the event actually executes, or after it executes, and precisely what action should be taken once triggered. There are two broad timing categories. Before triggers, run before an update, or insert actually takes place. For example, suppose your application's user interface represents data in one particular format, while the underlying database stores that same data in a different internal format. A user might attempt to update a value using their familiar format, but before that update is actually allowed to proceed, the value first needs to be properly converted into whatever format the database internally expects. A before trigger handles this beautifully. It recognizes that an update is about to happen, intercepts the incoming value, transforms it appropriately, and only then allows the actual update to proceed. There are several other reasons you might want this kind of pre-processing too. There's also a specifically important category called before delete triggers, kept as a distinct group precisely because deletion is inherently the riskiest of these operations. You're permanently removing something. So, a before delete trigger might need to check various conditions first, potentially raising an error, or otherwise determining whether that particular deletion should even be permitted to proceed at all. The second broad category, timing-wise, covers triggers that run after the event has already occurred, after an update, insert, or delete has completed. These after triggers might update other related tables to maintain referential integrity, check or transform related data for integrity purposes, or even perform operations outside the database entirely. There are other, less commonly used trigger types too, but I won't cover those here. Triggers can also be associated either with individual rows or with an entire SQL statement as a whole. If a trigger is associated with a statement, it fires once overall, applying broadly to every row affected by that statement's execution. If it's associated with individual rows instead, it fires separately, once per affected row. So if you execute a single statement affecting, say, 100 rows, and you've defined a row-level trigger for that event, that trigger will actually fire 100 separate times, once for each affected row, so you need to be quite careful and deliberate about which approach you choose. When writing your trigger's action logic, you can also refer to the affected data both before and after the change, typically by referencing something like an old version of the row or table, and a corresponding new version. Here's a concrete trigger example. As always, you begin with create trigger, give it a name, specify its timing before, in this case, and specify the triggering event, an update. So, 3 key pieces of information are established right away: are the trigger's name, its timing, and its triggering event. In this particular example, you specify that you're referencing the incoming, new version of the affected row, giving it a convenient alias. Then, for each affected row, you check that row's grade field. If it happens to be blank, you explicitly set it to null instead, before allowing the actual update itself to proceed. Otherwise, downstream update logic might not behave correctly if it encountered an unexpected blank value rather than an explicit null. You'd also typically mark this trigger's action as atomic, meaning it either fully completes or doesn't happen at all. It can never execute only partially. There's a somewhat more elaborate example as well, which I'll leave for you to read through and work out on your own. It's fairly straightforward conceptually, computing a student's total accumulated credits based on whether they passed or failed particular courses. Now, the real question becomes when should you actually use triggers? Triggers represent a genuinely powerful point of intervention, but there have been plenty of real-world cases where triggers were misused or applied in inappropriate situations, causing serious problems, particularly around performance. Some genuinely good use cases for triggers include logging changes into a dedicated history table, recording that some particular event occurred whenever that's important to preserve for later reference. Auditing user actions is another good use, recording exactly who performed a particular operation, so that person can potentially be asked about it later if needed. Other reasonable uses include automatically populating additional derived values in a table, enforcing referential integrity, recording login details, usernames, timestamps of operations, and performing simple data validation or basic sanity checks. These represent some genuinely appropriate, typical uses for triggers. But it's equally important, arguably even more important, to understand when not to use triggers. It's a bit like a well-known potato chip slogan: once you start, it's hard to stop. Once developers start relying heavily on triggers, there's a strong tendency to keep adding more and more of them over time, often well beyond what's actually appropriate or healthy for the system. So, let me highlight some important things you should generally avoid. You shouldn't create excessive numbers of triggers. They should be used quite judiciously and sparingly. Trigger logic itself should remain genuinely simple, never overly complex. Triggers should reference data across multiple separate databases or servers. Triggers definitely shouldn't call other triggers, creating cascading chains of triggered behavior that's a recipe for serious problems. Recursive triggers are normally disabled by default in most systems, and the default should generally be left alone. Don't deliberately enable recursive triggering behavior. You should also avoid invoking expensive operations, such as calling other functions, stored procedures, or views from within trigger logic, and you should generally avoid using loops or iteration within triggers altogether. The overarching goal is to keep your triggers smart, selective, and short, while still remaining genuinely effective as a powerful tool for maintaining your database's overall consistency. We're planning a dedicated tutorial specifically on triggers to go through additional details, walk through worked examples, and cover some case studies the teaching team has prepared, which will dive deeper into exactly how, and how not, to use triggers effectively. That brings us to the end of this module. We've covered functions and procedures in SQL, and we've also introduced triggers. Thank you very much for your attention, and I'll see you in the next module.